So in this video, we're going to cover the concept of position vectors, which is covered within your text in section 2.7. Now, why is this important? Well, one thing that you've seen a little bit so far, but you'll see a lot over the remainder of our course, is that one of the most common things we're going to do is to express a force in rectangular form, which means to take its magnitude and weight it proportionally along the I hat, j hat, and k hat direction. Now, oftentimes we're going to be dealing with forces that are actually applied by load-bearing objects like cables, where the actual direction of the force that cable exerts on a body is aligned along the cable itself. So if we had an ability to write an expression for the actual position of the cable, then we could take that and basically use it in order to decompose the force exerted by that cable on a body into rectangular form. And an example of that would be something like here, where we have a cable attached from a boat to a point along the shore, and it's being used to tug or pull that boat into the shore, so it's exerting a force on that boat. If I knew the magnitude of this force and I wanted to express that force in a rectangular form, if I had the capability to measure a three-dimensional displacement from the point of attachment to the boat to the point of attachment along the shore, what we'll see a little bit later on in this video is that if we can do that, we have the capability to decompose the force into rectangular form because of the fact that the force is directed along the cable itself. So just in case you don't remember from your calculus class, remember that if you have a three-dimensional coordinate system, and in general, we'll be consistent with our text, and we'll kind of call the coordinate two-dimensional plane in the base, x and y. And if I curl positive x into positive y, my thumb will point up to positive z. Recall that any point in this three-dimensional space can be described by a particular triple or coordinate pair, coordinate triple, I should say. And the way that I describe that is I start from the origin and I have a certain coordinate of x, and assuming it's positive, I'll move along positive x, say that's plus 3. And from that point, I can move along some direction in y, say it's positive, that would kind of move me to this quadrant of the xy plane. So say that I'm here, this much y, this much x. And from there, I can move up vertically. And I would describe this point by some coordinate x, y, and z. And again, since it's three-dimensional space, it will be a triple instead of just a double, as we would see in two-dimensional space. So say I called that coordinate b. I called that point b, and it's described by this triple coordinate x, y, and z. So just to kind of specify that I'm talking about point b, I'll put a subscript of b on there. And say in a similar fashion, I had some point in three-dimensional space a that was described by the actual coordinate triple xa, ya, and za. So say I wanted to describe a vector that described the displacement from point A to point B. The way that I would denote that is, first and foremost, I would use typically for the symbol of the vector an r. R's generally are associated with position vectors. And as a subscript, I would put A, B. And the actual order of that is very important. Since this is a position vector, these 2 points in the subscript tell me where I'm starting and where I'm ending. So if you notice, point A is the tail and point B is the tip. And if I want to write an expression for a position vector from A to B, the way that I do that is I take for each of the actual coordinates in the coordinate triples that describe each point, I'm going to take the x-coordinate of my actual tip, xb, subtract away the x-coordinate of my tail, xa, and weight that by the unit vector along the x-axis, which remember is I hat. I'll do the same thing for my y-coordinates, so yb minus ya, j hat. Same thing for my z-coordinates, zb minus za, k hat. And again, just one more time to be make sure no one's confused. The order matters here because you're subtracting, right? So you're taking the coordinates of the actual tip and subtracting away the coordinates of the tail, and that describes a displacement from A to B, or position vector R, A, B. So that's what this slide is actually showing you, but just in case it had been a while, I wanted to walk you through that, actually showing you on a dot cam. That is how you actually describe the position vector from A to B, assuming that you have coordinate triples for points A and points B. So how do you actually go about modeling a force using a position vector in order to model a force? Well, if a force has a known line of action and a known magnitude, and you can actually write an expression for a position vector along that line of action, you can always take and decompose the force into rectangular form by taking the magnitude, which here is denoted as F, and multiplying by a unit vector that's directed along the line of action from A to B. Now you might ask yourself, well, how do I go about getting this unit vector? Well, remember that a unit vector is nothing more than a vector with a magnitude of 1. So if you have an expression for the position vector RAB, like we did in the previous slide, you can always scale that by 1 over its magnitude. And then by definition, this quantity, RAB divided by magnitude of RAB, will have a magnitude of 1. So that's the way you can get a unit vector kind of directed along a particular line of action, AB. So in terms of an example problem, and this is a very common one that you would see in the text, say you have these two cables, both are connected at A, one goes from A to B, one goes from A to C, and we know the magnitude of the forces that are act in them. So in this case, the cable, which is connected from point A to point B, we're told that it exerts a force on this pole at this point of connection A of 840 newtons. And say we want to express this force in Cartesian form. And remember that Cartesian form is just another term that the book uses for rectangular form. Well, how are we going to go about doing it? Well, there's two things that we need to know, right? First and foremost, we know that since this is a force associated with a cable, the cable is exerting it on the kind of tip of this rod at point A. We know that it is directed along the line of action from A to B. So since we know the magnitude of this force, all we really need to do is get an expression for a unit vector from A to B. And the way that we're going to do that is to begin by developing an expression for a position vector from A to B. So we need RAB, and then from that we will go and scale it by its magnitude and get UAB. And once we have UAB, thinking back to this formula that I showed you on the previous slide, all that we need to do is multiply by that magnitude. So how are we going to go about doing that? Well, if you notice, fortunately, in our particular geometry, we're given enough information to actually write an expression for the coordinates of both point B and point A. And I'm going to kind of go to my .cam here, if I can find it here, hiding. Here it is. There we go. And I will scroll up just so no one gets confused by what we're talking about there. So looking back at our geometry that we're given here, how would we actually describe the coordinate triple of point A and point B? Well, let's start with A, because that's actually an easier one. And just look at our geometry. We won't redraw it. What do you notice about this pole? In terms of the XY plane, it's located directly at the origin of the XY plane. So in order to get to point A, I don't need to move any along X. I don't need to move any along Y. And I'm going to move in the positive Z direction by 6 meters in this case. So the actual coordinates of point A are going to be X coordinate is 0, Y coordinate is 0, and Z coordinate is 6. Now, what about point B? Well, one thing you might notice of that right away is it's actually located in the XY plane, I should say, right? In order to get to this point, I don't have to move any in Z. It's located at Z equals 0. So if you want, you can put that right in right away in order to make your life a little bit easier. And I'm going to zoom in just so I can be sure that everyone will see that. How do I get out here to point B? Well, notice first and foremost that I'm moving in the positive X direction according to the coordinate system that I was given. Specifically, now be careful, how far out am I moving? Well, you notice they've denoted that this displacement kind of away from the origin in the positive X direction is 3 meters. So it's going to be positive 3. Now, what about in the Y direction? Well, if you notice once I'm out 3 meters in X, I'm not going in positive Y, I'm going in negative Y. And I'm going in negative Y by 2 meters. So the Y coordinate of point B is going to be negative 2. And if I want to write an expression for the position vector from A to B, and the reason that I want to do A to B, you might ask, well, why not B to A? Well, look at the direction or the sense of this force. It's acting at point A, and it's directed along point B. So I need a position vector that also goes in that direction from A to B. So remember, the way that I'm going to do it is I'm going to take the coordinates of B and subtract away the coordinates of A. So 3 minus 0 is 3. For B here, minus 2 minus 0 is just minus 2. And then for, I should say that was for X, for Y, and then for Z, 0 minus 6 is just minus 6. And the way I usually check myself is I ask myself, if I were to start at A and go to B, is this the direction that I would go? So if I'm up here at A, how do I need to move in the Z direction to go to B? I need to move down 6. So that Z component should be negative, and it is. How do I need to move in X? Well, I need to move out in the positive X direction. So this X component should be positive, which it is. And which way do I need to move in Y? Well, I need to move in the negative direction. So this Y component should be negative, which it is. Now, how do I compute the magnitude of that vector? Well, remember, whether it's in 2 or 3 dimensions, the magnitude is always simply the square root of each component squared. Now, I can show the negatives if I want, but of course, when I square them, they actually won't matter. So this would just be the square root of 9 plus 4 plus 36, right? If I'm doing that math correctly. So this is the square root of 49. And of course, each of these quantities inside, since these units were in meters, are going to be in meters squared. And then when I take the square root, I'm going to get back to meters. So this is just 7 meters. Therefore, how do I get a position vector, or a unit vector, I should say, from A to B? And usually we show our unit vectors by having hats. We're just going to take our position vector from A to B and scale by its magnitude. So that just means to take this vector 3 minus 2 minus 6 and scale it by 7, which is just going to be 3/7 minus 2/7 and minus 6 over 7. And then I can express the force in terms of this three-dimensional, and it's called FB on the drawing, in terms of a Cartesian form, as the text is referring to it, by taking the magnitude and scaling the unit vector. And the magnitude in this case, we were told, is 840. So I'm just going to multiply that by 3/7, minus 2/7, and minus 6/7. And rather than get out my calculator, I think I have the actual results on our actual next slide, which we can see here. And if you notice, that is very similar. That is actually identical, of course, to what we had in the work that we did by hand. And if you do the math there, you'll see that this vector F has an x component of 360 newtons, a y component of minus 240 newtons, and a z component of minus 720 newtons. And you might ask, well, why does it turn out to have units of newtons? Well, of course, the magnitude of the force is in units of newtons. However, remember that when you add the position vector, where each component has a unit of whatever the physical dimensions of length are in the problem, in this case meters, when you divide by the magnitude of that position vector, which is also in meters, this unit vector from A to B will actually be unitless. So the product, when you scale this vector by a constant, will take on whatever the units of the constant are, which in this case are newtons. So hopefully that made sense for you and was a little bit of review in terms of describing position vectors, and I will see you in the next video.